compact bone on the side of bones. So what we can have is a disintegration of the epiphysis, and the joint actually collapses. And this is what happened to my grandmother. Unfortunately, it ended up killing her because she was super healthy and fit. Her bone broke under her own weight. She developed a blood clot and died 24 hours later, which was really sad because she was healthy and happy. But this can become quite a devastating problem. Yes.
So the triglycerides is all produced in the epiphysis. How far will it stretch down towards that?
Well, and now I'm about to explain that. If you look at orientated along stress lines, you see that term there? And that's what we see. And so how long will this is a really interesting thing and directly relates to each and every one of you. Whether you yourself break a bone or whether you're training somebody somewhere down the road that has had a bone break, it takes about 6 weeks to develop a soft callus in a bone. And it takes about another 6 weeks to begin creating a hard callus of a bone. And a callus is like what you'd think. It's a hard mass that develops. And the bone weaves at first to form this hard callus. But after all of that is done, and the bone is solid again, it takes up to 6 months for the trabeculae to realign. The trabeculae, remember, are for strength in a joint. Say, for example, you had been a runner for years, but you played hockey when you were a kid. And you decided, well, I don't want to run anymore because it's bothering my knees, so I'm going to start skating. And so you shifted from running to skating. It would take 6 months for all the trabeculae in the joints of your legs to align themselves to deal with the new forces that you're putting on there. That skating puts new muscle forces on the joints, so consequently, you would have to build greater strength in the epiphysis to deal with that greater force. So part of the idea of trabeculae is that every time you change what it is you're doing in your life, you have to realign the trabeculae so that it can most fully and completely deal with the stress loads you're placing on the bones. Yes.
So I'm just going to use CrossFit as an example here because they use such a wide spectrum of movements. So would doing that make your bones stronger, or would it just kind of make it worse?
Well, what it would probably do is it would probably say this. It would probably make it stronger in an overall sense, but weaker in any one given area.
Yeah.
You see what I'm saying?
Yeah.
So if you were, say, a lineman in football, and here you are, and this is what you do every week, boom! Well, then that's what you want to line up for. And you don't want to have it lined up for anything but that.
Yeah.
Right? Because otherwise that guy coming at you is going to break your leg. Right? So that's what you got to think about. So CrossFit is it's CrossFit. It's about being really quite fit at pretty much everything, but not as fit as anyone that would focus on any given part of it. Right? So that's really what it's about. So it is great overall. And for a general person, it's probably the best way to go. Right? Yes?
It just says how it's covered with endosteum, and you said endosteum is what produces osteoclasts that is eating away the bone.
Yeah.
So it's eating it away on the trabeculae?
Trabeculae. So it weakens the joint.
Okay.
So you can have, if you get osteoporosis bad enough, and this is what happens to a lot of senior citizens, it's when enough trabeculae has been eaten away within the bone that they'll be walking along and their hip will just disintegrate right as they're walking.
Right at the joint.
Right at the joint. The joint will just crumble up, crumble away, right? Because the trabeculae, so much trabeculae is lost that the epiphysis becomes too weak and can't handle the load. It just crumbles. So when we talk about compact bone. Compact bone has a central or Havisham canal, right? So this canal that goes right up the middle, like that. And then around each one of those, lamellar layers, which we know now, lamellar layers, each one laying down its proteins in slightly different direction to give great strength. And then we have what is called osteon or Havisham system, right? An osteon or Havisham system. And then perforating or Volkmann's canals. You see these ones that go crosswards like that? What they do is they perforate the edge. We have to get blood into these things, right? How we get blood in? So we perforate the bone. So coming from the edge of bone, from the periosteum inward into the bone are perforating or Volkmann's canals. And they also can join from one central Haversian system to another, which means that if something happened to your bone and there was a place that say this area here was damaged somehow in the bone, well, blood can still get up from there and would go up and go over and come down from there, right? So these Volkmann's or canals or perforating canals, they can share blood from one central canal to another. And of course, we can see on the edge over here, this is a perforating canal where it's bringing blood in from the periosteum into the bone itself. And of course, you know, when you think bones don't bleed in a way that's typical, they don't have a lot of blood in them. But I currently have a bone bruise in my right tibia. I was doing a lot of hiking, and because of my left legs had 5 knee surgeries, when I hike a lot on cliffy things, I always jump onto my right leg. And I guess I did a long hike and I did a lot of jumping, and I came up with a bone bruise on my right tibia. And the bone bruise means that within the bone itself there's bleeding, right? And it takes 6 months of practically no activity. I love to train my horses. In Kung Fu, your legs are your horses, your arms are your shoulders, your hands are your weapons. So I love to train my horses, my soldiers, and my weapons as much as I can. And this summer I couldn't train my horses, so my horses are weak. If I had to go into battle, I'd be going in on weak horses, and so I'm feeling vulnerable. So my soldiers right now are highly trained.
I thought he was a cat.
You have to think
like
like
horses
a
for a second. I was like,
Kung Fu
cool. I'll
person.
learn something.
But perforating canals then, they allow us, because what is the function of a perforating canal? You should have, like Simone asked a little while ago, so there's bone in blood, or there's blood in bone? He was curious, there's blood in bone. You want to know how, of course, it functions. What is functioning to bring blood into the bone, right? What is causing that to occur, right? How does the bone get in there, or how does the blood get in there? So perforating canals, blood vessels from the periosteum penetrate the bone. That's how the bone is receiving. From the periosteum, it's receiving blood. Just like the periosteum is causing the development of appositionally by releasing osteoblasts, it is also bringing in blood so that it can be innervated. So nutrients and waste travel to and from osteocytes via the lacunae and canaliculi, right? So the lacunae and canaliculi, again, the lacunae function as a house. That's where the cell lives. And the canaliculi is the transport canals which bring material from one cell to another. Like England did when they developed their canal system. It was a system of little canals, canaliculi, that connected all the cities of the United Kingdom one to another. And then, of course, from osteocyte to osteocyte, by gap junctions, we communicate. So this brings us to the idea of intramembranous ossification and endochondral ossification. We talked about this a little bit in the lab, and I said that intramembranous ossification is the idea that all bone except for long bone is produced within a membrane, right? And then endochondral takes place within a cartilage. So that's the difference. Intramembranous takes place within a membrane, and endochondral within a cartilage. Endochondral ossification is long bones only. Only long bones are produced by endochondral ossification. The other 3 bones, short, flat, and irregular, all produced by intramembranous ossification. What is the function of intramembranous ossification? The production of short, flat, and irregular bones. What is the function of endochondral ossification? The production of long bones, right? So, intramembranous ossification, as we said, takes place in connective tissue membrane formed by, of course, embryonic mesenchymal cells, right? It forms all the flat bones and short bones, etc. So things you need to be aware of, centers of ossification. These are locations where membrane ossification begins. In an intramembranous ossification, between two, like looking at an envelope, right? somewhere in that envelope, you dropped a quarter. That quarter inside the envelope is the ossification center. And from that quarter, the bone or the envelope will fill, right? That's what we're talking about. And then fontanelles are just large membrane-covered spaces between developing bones. So in a baby, before the bones come together, there's a soft spot, right? A fontanelle. These are simple terms that you can know. And here we see, there's the ossification center, there's the membrane, and this is the parietal bone development. Here is the ossification center here, that's the membrane, and it's the frontal bone that's developed. As the bones come together, at some point there'll be a space between them that is not bone, and that will be a fontanelle. So endochondral ossification, bones at the base of the skull, part of the mandible, any long bone, beginning at about week 8, so about 8 weeks into your fetal development, you start to see the bones development, and some does not begin until 18, 20 years of age. So ultimately, let's go way back. There we go. Little baby. And the little baby, we can see that, remember that every one of these spaces that is just a white space, that means it's still cartilage. Where we see red, dark red is solid bone. Light red is bone still that hasn't quite solidified. So here we see light red where the bone is not quite solidified. Where here we see dark red and we can tell that the bone is quite heavily solidified. That the hands, there are parts that are and parts that are still totally cartilage. Right? Parts, you can see the epiphysis of these bones are still quite cartilaginous. So that's what we're seeing, this idea that on our endochondral ossification, that the bone at the beginning is cartilage. So here we see, what is the thing that begins this whole process? That when you're a baby, your bones are covered with perichondrium. At some point along the way, starting 8 weeks in for some bones, that perichondrium turns into periosteum. And it's at that point in time, it's at the moment that perichondrium becomes periosteum, at that middle part of the bone, in this primary ossification center, here we see periosteum is developed, that's where osteoblasts are released. And we begin the process of producing bone. So this is calcifying cartilage. The calcifying cartilage represents the epiphyseal plate. And so it is cartilage in front of it, and it's bone behind it. So as the bone develops, the cartilage ahead of the bone is the plate, and it will keep growing forward, producing bone behind it. So when we look at this, we can see here would be just cartilage itself. Here is the primary ossification center. What we're seeing now is in order for the epiphysis of every bone, which is different, right? The hips, the trochanter and the head of the hip is quite different than the condyles of the tibia. So each epiphysis is quite different. So it needs a secondary ossification center. And that's what we see here. This is the primary ossification center. Each epiphysis has its own ossification center, and those are called secondary ossification centers. So what is the function of a secondary ossification center? To produce the epiphysis. What is the function of the primary ossification center? To produce the diaphysis. Right? So primary ossification center produces the diaphysis of a long bone, and the secondary ossification center produces the epiphysis of a long bone, the joint, if you will. And for those 420 fans, that's something different. So endochondral ossification. This is the end of it then. We come to a point where the bone has developed its epiphysis. The bone has reached the length that the DNA suggested, and without some epigenetic event that caused you to grow taller, then you would stop. And And once that happens, you have calcification of the growth plates and a mature bone, an epiphyseal line instead of an epiphyseal plate, and the end of the length of bone, growth in length. So we talked about appositional growth being growth outwards and interstitial growth being growth between healthy cells. So that's growth in length and width, right? Appositional growth is wide and length is endochondral. Once the endochondral growth has stopped, the only type of growth that is left is interstitial, and that's between cells, and appositional, and that's on the outside. The closure of the epiphyseal plate, of course, is the ossification of the plate, which leads to an epiphyseal line. And that, depending on the bone, the longest bones, the femur, take the longest time. So if an epiphyseal plate is still existing within you guys, it will surely be your femur will be growing still. And depending, your arms could still be growing. So articular cartilage does not ossify and persist throughout life. So the hyaline cartilage that forms the articular cartilage on the end of bones never leaves until you die. And then even then, it takes a while before it disintegrates and is gone. When we look at, from a figurative perspective, this is the epiphyseal plate right here. Or pardon me, the plate right here, but this is the epiphyseal side. Epiphyseal side meaning this is the side that's purely cartilage. This is the diaphyseal side. This is bone now. So the epiphyseal plate, as it moves up through the bone, it's heading into cartilage, and it's leaving behind the bone. This always reminds me of a paver. And on the weekend, I was trapped out at the Guy Chosen Cafe for about 20 minutes while this paving machine did its job. And of course, I think about this whenever I watch the paving machines, because the truck comes along and it pours the pavement into the paving machine. The truck gets put into neutral, and the paving machine just continues to push the truck forward as the